Picture a brand new analytics platform. It tracks real-time sales, and right at the center is a leaderboard showing the top 5 performing products. At launch, when the user base is small, this leaderboard updates instantly. A few dozen sales roll in, the numbers tick up, and everything feels incredibly snappy. Behind the scenes, the database is doing something incredibly straightforward. Every time a new sale occurs, it takes the entire list of products, sorts them all from highest to lowest, and simply slices off the top 5. With a few hundred items, sorting the entire list takes fractions of a millisecond. It's a perfectly logical solution for a small, static dataset. Then, the platform goes viral. Suddenly, that tiny stream of sales data turns into millions of events per second. The database is still trying to sort every single item every time a new event arrives. The servers redline, the dashboard freezes, and the entire application grinds to a halt. Sorting an entire dataset operates on a steep curve, big O of n log n. As data volume grows, processing time spikes. The system wastes CPU power organizing a million-item tail, only to throw it away because we just need the top 5. To survive this level of traffic, we have to stop organizing the noise entirely. We need a way to filter the data without sorting it. The solution to this bottleneck is a specialized data structure called a Min-Heap. It sounds a bit backward at first. If we want to find the top 5 largest sellers, we actually use a Min-Heap restricted to a size of exactly 5. Think of this VIP lounge with exactly 5 seats. Members organize into a tree hierarchy, with the lowest score at the front door. Because of how a Min-Heap works, this absolute smallest item is perfectly positioned at the top root node, acting as the bouncer. By capping the size of this tree at k, in our case 5, we completely eliminate the need to sort the database. We turn a massive organizing task into a simple, highly exclusive membership test. When a new sale comes in from the stream, it doesn't look at the whole dataset. It walks right up to the root node and compares its score to the bouncer. This takes exactly 1 step, mathematically known as constant time, or O of 1. If an incoming score is lower than the bouncer, it's instantly discarded. But if it's higher, the bouncer gets evicted. The new data takes the top, performing a rapid sift down. It cascades down, swapping places until the new lowest score becomes the new bouncer. When the user actually wants to see the leaderboard, we pull the 5 items out of the heap. Since a Min-Heap naturally empties the smallest items first, we simply reverse the list to show them from highest to lowest. These continuous, tiny adjustments ensure that the true top performers are maintained effortlessly, no matter how fast new data pours in. If we look back at our analytics dashboard now, it is running perfectly. The servers easily handle millions of events per second, and the leaderboard updates without a single stutter. The processing time to handle all those events has dropped from that steep n log n curve down to O of n log k. We are doing a microscopic amount of work for each incoming item. Our system resources highlight how we solved the memory problem. Notice how the memory gauge is locked exactly at k. Whether the database holds 100 items or a billion, the memory footprint for finding the top 5 remains completely flat. Replacing brute force algorithms with a dynamic filter is the exact difference between an application that crashes under pressure and enterprise-grade software that scales. By capping our working memory at a fixed size, we unlock the ability to process continuous, boundless streams of data. The stream never has to end for the math to work. At a truly planetary scale, however, even the memory used for counting becomes a problem. If you're tracking every unique hashtag or search query on the planet, the list of items itself can eventually exceed your available RAM. To survive this, engineers use probabilistic tools like the CountMin sketch, which estimates item frequencies using only a tiny fixed-size grid of counters. But even when the counts themselves are estimates, the core mechanism for finding the leaders stays the same. Those estimates are fed directly into the bounded heap we've built, which still acts as the final arbiter of who makes the cut. High-performance data engineering is defined by how early and how efficiently a system can discard the noise. By ignoring the millions of irrelevant data points, we can finally focus on the handful that actually matter.